Hello, I'm Dan. I'm going to be speaking to you today about the power and pains of smartphone sensor data. So a little bit of background. I'm a data scientist at TrueMotion. At TrueMotion, we develop smartphone apps to make driving safer and more affordable. We build smartphone apps that can track how good of a driver you are based on the sensor data that we collect from smartphones. We use this information to give you feedback on your driving and help you improve. And we also work closely with some of the largest insurance companies in the world, such as Progressive Insurance, to develop programs, usage-based insurance programs by which people can download our apps, track their driving, improve their driving over time, and get discounts on their car insurance. So I'm going to talk today about particularly smartphone sensors and the algorithms that operate on them. But I just want to start with saying that sensor data is everywhere. We're really in the age of data in general, in the information age, but few sources of data have as real, powerful impacts as sensor data. And there's sensor data coming from all of the devices that you use. Your car has sensors in it, your smartwatch has sensors in it, your phone and your iPad. We're moving towards a time when your refrigerator and microwave and all kinds of home appliances will have sensors as well. And they're going to use data and information from these sensors to improve your life, to learn, to understand, and to develop better usage practices. So to provide a little bit of motivation about why smartphone sensors are helpful and important, about 70% of Americans have smartphones. I mean, that's significantly more common than a college degree. People spend 5 hours a day interacting with their smartphone. That's pretty crazy. It's a pretty crazy statistic. And you're not just getting sensor data from your smartphone while they're interacting with it. People carry them around with them everywhere they go. I mean, I've got my smartphone on me right now. I'm sure probably most of you have your smartphones on you. And everywhere that you go, it's gathering data. It's getting more information that data scientists can extract powerful insights from. The other reason why smartphone data is really interesting is the variety of different types of sensors that our smartphones equipped with. And we're going to talk about each of the different types of sensors, or actually really just a subsection of them in detail, but this is just a short list of the types of sensors that are in most smartphones. A variety of different types of motion sensors, GPS, and compass, and magnetometer, thermometer, barometer. So let's just go into some of the specifics of these different types of sensors. So probably one of the most useful types of smartphone sensors, and this obviously is not smartphone specific. There's probably one of the hottest topics in data science is GPS data and what you can get from GPS data. With a GPS, you can understand everything about what a person does every day. You understand where they go, you understand how long they spend there. And not just on a single person basis, but on an aggregate basis. You understand what are the places that people tend to go, what time they go there. This is useful for optimizing systems. You could think about civil engineering, optimizing roadways, or even personalized recommendations and things like that learn based on the places that you go, the places where you spend time. Gyroscope and accelerometer. These are a few of the motion sensors that your phone is equipped with. These are 2/3 of what's generally referred to as the IMU that's within your smartphone. That's a set of motion sensors from which you can get a good sense of the position of the smartphone in space and what kinds of accelerations and external forces are acting upon it. And you can use this information to determine where the person is holding a smartphone, what the smartphone's doing. Activity recognition is a pretty hot topic that lets you understand how a person might be exercising or what place a person might be in. It also helps with tracking and can support the GPS in a lot of situations. At TrueMotion, I'm going to talk about this in a little bit more detail later, but we use smartphones to understand how people drive. We use the motion sensors to understand how people drive and detect different kinds of dangerous driving behaviors and distracted driving just based on the movements and the components of the acceleration on the smartphones. And to give a little bit more color on this, the magnetometer is the other component of the IMU. And when you integrate the magnetometer with the gyroscope and the accelerometer, you can get a better absolute sense of the orientation of the phone with respect to the Earth when you incorporate information from the magnetic field of the Earth. And you can also use it for your compass. That's how your compass in your phone works. Also, there's some slightly cooler things you can do with the magnetometer if you're a little bit creative. When you turn on a car, you're going to see a spike in the magnetometer when the engine starts running. When you go under a power line, you're going to see a spike in the magnetometer. If you're pretty savvy and you think that you've got the ability to do some pretty cool signal processing and machine learning, you could maybe build a smartphone application that can tell a person how much time they spend under power lines, or what the strength of electric fields are where somebody is, if you're one of those people who thinks that electric fields might cause cancer or something like that. The barometer also is another one of the core sensors in the smartphone. It's usually used for altitude detection. You can tell how high somebody is based on their air pressure around them. You can also use it for a number of kind of cool applications. The barometer will change its readings when somebody's inside versus outside. If somebody's driving in a car, you're going to see a spike in the barometer when they open up the window, especially if they're going pretty fast, and the air pressure will normalize faster. Thermometer helps with that as well, also for kind of weather understanding. You can also, with a thermometer, tell what type of surface the phone was placed on. If a phone was in somebody's hand and they placed it on a surface that conducts heat quickly and the phone changes temperature quickly, you might be able to ascertain that. And you could imagine what kinds of smartphone applications might benefit from having this kind of information of what sorts of places a person might be putting down their smartphone, or even tell when it's in somebody's hand. There's a litany of other types of sensors that are in your smartphone. I'm just going to go through this short list of some examples. The Bluetooth sensor, which is not really a sensor, can let you know what other Bluetooth available devices are nearby, which could give you a sense of how populated a place a person is in, or what types of devices are near them. The camera, of course, is equipped on most smartphones. Most smartphones won't let you access the camera without the user turning it on manually or opening the app manually, but even that can be pretty useful for getting glimpses of a person's environment. Microphone is similar. Some apps will let you, or some OSs will let you turn the microphone on in the background, which could help you get some pretty cool understanding of a person's surroundings. One kind of interesting idea that I came across was using a microphone as almost like a personal diary. Just records your last hour of activity and writes it down. And so if you're in an argument with somebody and they're like, I didn't say that, you say, oh, yes, you did. So ambient light sensor, that's just another sensor that can be pretty useful to tell if the phone is out or in. You even tell how long somebody might spend outside using something like that, get better sense of what type of person somebody is based on that. Wi-Fi and cellular signal. I'm actually going to give a bit of an example on this one a little bit later, but the Wi-Fi and cellular can be really useful for situations when you don't have as strong access to the GPS. Based on, if somebody's moving, you'll get cellular signals strengthening and weakening, especially if they're moving a reasonable distance, based on what the nearest cell phone tower is to them. And with that information, you can triangulate their position and their speed, even if you don't have direct access to the GPS, if you need to turn off the GPS for purposes of battery or something like that. And you do similar things with Wi-Fi. So here's a kind of interesting company that I came across. They use a lot of smartphone sensors to get hyper accurate weather predictions. That it's kind of crowdsourced weather. Crowdsourced sensor data is kind of a hot topic now also. Think about predicting weather. You've got a weather tower you put up somewhere where you got enough space to put up a weather tower, and you're going to have to make predictions of the weather based off of the recordings of this tower. And those predictions might be for the 10 to 15 mile radius around this tower. And you're not going to be able to get super localized weather. Because sometimes it's raining in one place and it's not raining a few miles away, or it's temperatures, differentials, and things like that. But if you've got like 100,000 sensors, every single person with your app has a smartphone and they're at a different place, and you get super localized barometer and thermometer readings, even if these are way lower accuracy than what you're going to get from a weather tower and much more variable, you can get, they claim that they can predict rain beginning down to the minute. I'm not sure if they can do that, but that's a pretty cool claim, and I wouldn't be surprised if they could do that now or at some point in the future. I think I'll take a stop now. If anybody's got any questions, just one or two. Okay, we'll have time for questions at the end too. So I'm going to dive a little bit deeper into GPS and motion sensor data. I'm going to start with GPS, then go to motion sensors. So just a sense, for those of you who haven't worked with GPS data before, the sense of what format you can usually get it in from a smartphone. You usually come in a vector of latitude tuples, longitude tuples, speed values, bearing values. You get a number of other things like accuracy and stuff like that. And so the problem of analyzing GPS data is the problem of analyzing multivariate time series data. So some kind of cool examples of applications of GPS data. Well, first, just the general GPS data workflow if you're going to build a GPS data application. You start with your raw GPS data, and then you might send over to a map provider who's got locations of roads, businesses, different pieces of information like that that might be useful for getting a better sense of what's going on in your GPS data. If you want to do road snapping, for instance, if you have a bunch of latitude and longitude examples and you want to figure out what road somebody was on, or if you want to know what kind of businesses they were near, then you have that augmented GPS data. You do data science on it, and somewhere down the line you profit. So one cool example is the Foursquare and Chipotle situation that happened, I think, about a year and a half or 2 years ago when Chipotle had its E. coli fiasco. Foursquare published some analyses they did on people going to Chipotle and how often they recorded locations of people who had gone to a Chipotle. And they were able to predict very accurately exactly how much Chipotle's stock would fall based on the decrease in number of people going to Chipotle, just from GPS data and analyzing that. At TrueMotion, we do a lot of work with GPS data. It can be really useful if you understand what sorts of trips are somebody's commutes, where somebody's home might be, where they work or what they do there, from understanding how long they spend in places and whether they're moving. You can also use GPS data to predict brakes, actually, just from looking at speed traces and doing some intense data science. You can get hard brakes out of raw GPS speed data. Another application that's a little bit more science fiction on the dystopian side would be getting a character of the sort of person that somebody is based off of the amount of time they spend in bars versus in gyms, or in parks versus in liquor stores, or things like that. You can imagine all sorts of Orwellian situations where information like this could be used against us, or for us. So GPS is not a panacea. It has a lot of problems, and one of the biggest problems is that GPS is hungry for battery. If you've got an app that's just that's just constantly using somebody's GPS, you're going to drain their battery down to zero very quickly. They're going to uninstall your app, and you're not going to be able to get any data. This is a problem that any sort of GPS app developer needs to incorporate, and it's often solved by really selectively choosing when you want to gather GPS data and how intensely you want to gather it. If you want 1 hertz GPS data, so that's once every second, that's tough to be able to do for an extended period of time. But if you want to ping somebody every 15, 30 seconds. You can do that. It's a lot easier. And it depends on your application. If you're trying to predict hard brakes, like at TrueMotion, we really need as high fidelity GPS data as you can get. If you're trying to get a sense of how much time somebody spends in different places or whether they're currently moving or something like that, 15 to 30 seconds will probably get you where you need. So let's talk a little bit about motion sensor data. So a lot of analysis of motion sensor data really is focused on the, yes? Yeah.
So are you able to have variable levels of data that the device produces? Like, let's say you see the guy's driving and his phone's plugged in, so grab more data. You see someone's battery's at a lower level, grab less data. Kind of big variable levels, depending on how much data you need to get the best picture of the person versus their phone's battery level and whether they're plugged in or not.
Yes, so I mean, the easy answer to that is absolutely. Both of the situations that you just described, we can absolutely do. However, there are some caveats. Sometimes people have certain permissions that are set that make it harder for you to get as much GPS data as you need. Another situation, if there's other apps that are also using GPS, you might get a higher frequency than you ask for, just because there's something else that's already set the frequency up to a certain level. But in general, yes, we can usually modulate it. It's also OS specific. What iOS lets and what the 10,000 different types of Android let can vary. Cool. So motion sensor data. As I was saying, the gyroscope and the accelerometer are the main sources. And usually when we interpret them, we want to run through some sensor fusion algorithms. Because by themselves, any motion sensor has a lot of problems of noise we're going to dive into in a little bit. But these problems can be really minimized, and we can get the most out of this kind of data if we incorporate information from both sensors and fuse them appropriately. So here's just the way that we would think about a device's orientation in space by using the accelerometer and gyroscope. There are a few different representations that we can have. So just to be clear, these are the way that we would solve the problem of, I have this trace of motion sensor data. These are a bunch of numbers. How do I interpret these numbers and think about these numbers in a way that lets me know what was the orientation of the phone with respect to gravity as it was turning around or facing up or facing down? And so here are three representations that we could use. So probably the simplest to understand, the simplest to work with, is the gravity vectors. So this is just you have the x, y, and z axes of the phone. And this is just the magnitude of the gravitational acceleration along each of these axes. So if you've got a really strong z and a weaker x and y, then your phone's probably in this sort of position with the z-axis aligned with gravity. If you got a really strong y-axis, your phone's probably like this. For our situation, if we're trying to get a sense of what somebody's phone is doing in a car, this is really useful if we want to know, say, is the phone in a mount? Well, if we've got the position of the phone looking like this, then there's a decent chance that it might be. It's also useful for understanding, of course, the physical activity recognition type of problems. If you're trying to understand whether somebody is performing an exercise correctly, for instance. They've got their phone strapped in on their arm, and you monitor these motion sensors, you can get a pretty good sense just based off of the fluctuation in this position, what is the position. So another way of representing pretty much the same thing as the gravity representation is using Euler angles. So these they come from aerodynamics, the yaw, roll, and pitch, which gives us a sense of what are the rotation about these different axes, around the same axes, the x, y, and z axes. So as an angular representation, I think that most people would think this representation is a little bit less intuitive than the gravitational representation, but it's useful for a lot of applications. It can represent movement a lot better than the gravitational representation. If you want to represent a phone turning in a circle, the gravitational representation will have a number of the different angles changing at a slightly harder to understand and harder to classify way, whereas the Euler angle representation is very clean. Unfortunately, Euler angles suffer from a problem called gimbal lock, which essentially is when the orientation of the phone is aligned with one of the axes. You can't distinguish rotation about the other two axes. A representation that solves that problem is quaternions, which some of you might be familiar with from computer graphics or if you've done motion sensor work before. Basically, the quaternion representation is it's 4 numbers. There's x, y, and z, and a w. And the x, y, and z represents a vector, and the w represents a rotation about that vector. So quaternions are good because they're the most unambiguous of the 3. They capture the most information, and they can clearly represent any type of rotation in space. They're bad because they're really hard to interpret for most people. At least for me, I find them. When I try to interpret quaternions, I've got to rotate it back into gravity, usually. Algorithms generally will work on any of these 3 if you're training a machine learning algorithm on them. There are some problems, though, with smoothing and filtering that will happen with quaternions. You can't use a linear filter. You have to use a special quaternion-tuned filter if you're going to be smoothing quaternion data. So sometimes it's helpful to smooth the data while it's still in the gyroscope and accelerometer form before transforming it to one of these representations to avoid that problem. So just to get, I know that was a lot and kind of complicated, especially if you haven't worked with this type of data before. So I'm just going to go into some little bit more concrete examples of how this information is useful and how we use it at TrueMotion. So one problem that we solve at TrueMotion is the mode of transit problem. So that is, we see that somebody has gone on a trip. We've seen from their GPS trace that they were moving at a pretty reasonable speed that's representative of moving in a vehicle. How do we know what type of vehicle they were moving in? Was it a bicycle, a train, a bus, a car? And we have a whole bunch of algorithms to do this. We've got a team of data scientists working on this problem. And one pretty cool algorithm that we use is bike classification, which we can do by looking for particular sequences of fluctuations in the motion sensor trace. So this is a gravitational representation. And you can see when somebody's pedaling, the up and down motion of the pedal appears directly in the gravitational representation. And in order to see this, in order to get this, we actually need to first align the phone with respect to gravity. Because the phone might be in the person's back pocket, they might be in the front pocket, they might even be in a coat pocket. And in all of these different situations, it's pretty common that you're still going to see that kind of up and down pattern, unless if it's in a backpack or in the front pouch of the bike. But if we rotate the phone to orient it with gravity first, then we can see this kind of pattern. And in practice, this is usually done with a nonlinear machine learning classifier. They'll be trained on short sequences of sensor data. And I'll get into some cool algorithms that we could use for that in a little bit. So another problem we solve at TrueMotion, one of our bread and butter, is figuring out dangerous driving. So this is an example of dangerous driving that we would want to be able to detect. And we use both GPS and motion sensors to detect dangerous driving. I'm going to talk about one pretty cool algorithm that we can do with motion sensors. And that's phone-car alignment. So if we go back just a few, I've got this picture here. If you just look at this picture of the phone, you can see that we've got the X, Y, and Z axes of the phone. And when the phone is in a car and we're moving the car, we're going to see the accelerations along the X, Y, and Z axis. But this does not give us direct, really deep understanding of what was happening to the car. If we see some strong acceleration along the x-axis of the phone, well, that could be a hard brake. It could be a harsh acceleration. It could be a turn, centripetal force. It could be somebody dropping the phone. It's tough to understand that without knowing, first, what is the orientation of the phone with respect to the car? And then, given that orientation, what are the different types of accelerations that we're looking for? So in order to perform this rotation, which we are pretty much just finding a rotation matrix between the axes of the phone's acceleration and the axes of the car's acceleration. We could use an algorithm called PCA, which probably most of you are familiar with. So just to take a step back, the goal of aligning with the car is to figure out what is the acceleration along the longitudinal and lateral axes of the car. So when a car brakes or accels, you're going to see accelerations along the longitudinal axis of the car. When the car takes a turn, you're going to see accelerations along the lateral axis. It's going to be your centripetal force. And as a car moves, most of the accelerations that it experiences are along one of these two axes. So the maximal variance of the acceleration points actually is along the longitudinal and lateral axes. So when you perform PCA on a long sequence of acceleration points, the first and second principal components are usually, not always, representative of the longitudinal and lateral axes of the car's acceleration. And we've done a lot of experiments to confirm this with external accelerometers that are mounted to the car, and then comparing it. Some of the really hard problems are distinguishing between the longitudinal and lateral acceleration. Do you have a question?
Yeah, so if someone is not necessarily driving like in order to fast pace, but they are in order to pass carefully with road traffic, is that detecting that necessarily that much more?
So is your question how would you compare somebody's driving with respect to the traffic around them? Yeah, so there's certain patterns of driving that are indicative of risk that are not necessarily speed-based. They have to do with quick changes in acceleration or sharp rotations that would be due to sharp turns. And these have been studied extensively by a large number of large insurance companies, and also with some long longitudinal studies over several years with cameras in people's cars, understanding what their behavior is. And so I think what you're asking is 80 miles per hour driving is not necessarily dangerous if everybody around you is going 80 miles per hour. And that's correct. But dropping in speed by 25 miles per hour in the course of a second is dangerous driving, regardless of what everybody else around you is doing. I think that this pretty much covers the PCA for phone car alignment. Yes? Are you asking if we've explored other options? Yeah, so actually, like a random forest to directly predict the rotation matrix is a pretty good solution, and we've explored that. We've explored a number of different options. There's a few reasons why we like PCA. Actually, our state-of-the-art uses an augmented version of this, but it's not patented, so I can't talk about it. But our PCA is patented, so I can talk about it. But the random forest is, in general, when you're solving any machine learning problem, if you have a solution that's relatively simple and linear, and this is a linear problem. It's just a rotation. It's expressed in the matrix multiplication. So a nonlinear algorithm like random forest is a little bit overkill a lot of the time, but it is still useful, and it can be really useful actually in the case where you have a rotation matrix that's changing because somebody's rotating the phone in their hand or picking it up and putting it down multiple times. But gathering sufficient labeled data for that with external accelerometers on cars and getting a sense of what somebody was actually doing with the phone is a difficult task. Yes?
Can you detect if somebody is reading their phone while driving?
Yes, we can. That's not this algorithm, but we can do that. What's the
percentage you see?
Of what people are reading their phones while driving?
Yeah.
So we publish our distracted driving statistics constantly, so I've got these on the top of my head. It's around 18% of people who will be doing what we call non-call active phone usage, which would incorporate reading your phone while driving or tapping on your phone screen and other similar activities. We can distinguish between reading the phone while driving and tapping on the phone screen, but I don't have the statistics for how that breaks down at this moment. So 18% of all driving time is performed while people are performing those activities on the population at large. However, people who've downloaded our TrueMotion family app decreased that number to closer to 9%. Yes?
How would you differentiate between, say, I'm driving the car versus I'm sitting in an Uber?
Yeah, so that's probably the toughest problem that we solve. It's the driver identification problem. We have a large ensemble of different algorithms that are tuned for solving that problem that range from everything to modeling your behavior and understanding how you typically drive, to modeling how you get out of the car and understanding whether you got out of the left door or right door by performing an algorithm similar to this one, and then checking the different rotations that your phone experiences. Yeah.
And what checks do you have, like, say, if I'm in a hurry and I just turn off the phone or...
Yeah, so we'll see that if you turn off your location services, and there's obviously patterns of someone who tends to turn off their GPS at this hour or this amount of time. We can see that kinds of information, and that gets reported to insurance companies who would then incorporate that in their pricing models. I'm just going to answer the rest of the questions at the end. So I just don't want to have slides remaining. So let me just talk a little bit briefly about handling noise. So anytime you do anything machine learning, you're going to have, or signal processing, you're going to have problems where your data is noisy. And in the case of motion sensor and GPS data, especially from a smartphone, which generally has kind of lower quality sensors, your data is really noisy. And so I'm going to talk about two main types of noise that you might see in time series data and sensor data in particular. The first is mean zero noise. So this is usually characterized as Gaussian noise, but it's not always Gaussian. We can deal with mean zero noise in two ways. There's linear smoothing kernel, like a Gaussian kernel or a rolling mean type of solution. And there's median filtering. So when you've got this kind of salt and pepper noise that you would see in like an image, that a median filter works pretty well. That just takes the median of nearby points and replaces each point with that. This is a nonlinear. Whereas if you have that sort of Gaussian noise, a linear convolution kernel tends to work a little bit better. And often for most applications, you'd want to try both. So a fundamentally different type of noise is systematic inaccuracy. And this would be noise that would bias the mean, so it's non-mean zero. And this is usually caused by a miscalibration of sensors, some bug in the code that happened a while ago, but now all your system's built around it, so you can't fix the bug. All kinds of weird issues that might bias the mean. And most sensors have both of these problems to differing degrees. And to address systematic inaccuracy, you can't really smooth it. That won't really help. It's often helpful to bring in information from another sensor. If you can recalibrate the sensor, but if it's someone's smartphone, you can't always do that. So the Kalman filter is an algorithm some of you may or may not be familiar with. It's pretty simple algorithm at its core that just bases around fusing multiple sensors and understanding getting the best possible estimate of the state of some system by incorporating as much information as possible and balancing out random noise and systematic inaccuracy from multiple sensor readings. It's fundamental. At its core, it's similar to the concept of ensembling classifiers or diversifying investments. So just to make that a little bit more concrete, let's say you were trying to track an airplane, and you had a GPS in the airplane, and also motion sensors. And so at each point, you can read its motion sensors, and you can tell, all right, well, it's got this velocity, it's got this acceleration. I think at the next time step, it's going to be at this spot. And at the next time step, you have that reading from the motion sensors and your prediction that you've made from that, from your physical model, as well as the GPS reading. And the Kalman filter pretty much thinks, oh, well, I've got this reading from the GPS and this reading from the motion sensors and my physical models. Well, let's try to weigh how much I trust each of these different readings and find a good midpoint that I would take as this is the Kalman estimate for your position. And this tends to work pretty well when you've got more reliable sensors and you've got a good sense of how accurate your different sensors are. This sort of strategy is pretty reliable. And there's other similar filters that are pretty popular, like the particle filter for solving the same problem. So just for the more mathematical of you, you might know that the product of two Gaussians is a Gaussian. And if you have Gaussian noise from, or like an estimate that's biased by Gaussian noise from one of your methods of finding the position, and another Gaussian that's orthogonal to that, that also has noise of finding the position, and these are totally uncorrelated, then the product of those Gaussians will have a much smaller covariance than either of the two of them. And that's the sort of the fundamental explanation for why the Kalman filter works. If you can assume that the types of errors that the two or more sensor readings have are uncorrelated, then their product is going to have lower covariance. You get a more accurate estimate. So I'm just going to talk about how we can classify sensor data. And I'm going to talk about it through the framework of these guys. This company, Amigo. They make a wearable that can track what swim strokes you're doing in order to give you a sense of how good of a swimmer you are or what your times are. The thing even help you with your form. I've never used them, but I thought they were kind of interesting as a framework for this talk. So let's think about, what's the fundamental problem here? We're trying to identify a swim stroke. So this is the butterfly stroke. It looks something like this. I can't do a butterfly. But if you're trying to classify a butterfly and distinguish it from, say, like the breaststroke or the freestyle, you'll want to get a sense of, well, what's the systematic motion that's happening? What's the orientation of the wearable at different points in time? And build a classifier by doing that kind of modeling. And so there's a few possible approaches to doing this. So probably the simplest approach is just, all right, well, we think maybe this swim stroke takes about a second to perform. So let's segment our time series up into 1 second or second and a half or whatever segments. Let's compute some summary statistics over each of the different motion sensor channels for these different periods. And then let's just train the random forest on those summary statistics. So here's what that looks like. You've got your time series that's tracking motion sensors, and you just convert it to summary statistics. I think in this case, these are the first 4 moments of frequency, then the median, min, and max. But you'd pick your own types of summary statistics based on your application and what you're trying to do. As what you're trying to do is more complicated, you might want higher order summary statistics. You can take Fourier coefficients. Usually works pretty well for some applications. And this is nice because it's kind of out of the box. If what you're tracking is some short event in time series, it works pretty well. This is a great first option. And for more complicated things, it doesn't always work. So here's another application that's pretty cool, another algorithm that we could use. So this is dynamic time warping. And this is sort of, for those of you familiar with Levenshtein distance, the edit distance of 2 words, that's pretty much what dynamic time warping is, except for a time series. You try to figure out how much moving around of this series would I need to do to make it match this other one. And so this is cool for time series where they're not aligned, or if they're both have like a pretty similar pattern, but they're off sync, or one's phase is a little bit lower than the others. Dynamic time warping will help you capture that. And this is actually pretty useful for the byte classification problem that we showed earlier, using this kind of mapping, even if things aren't perfectly aligned. And if you want to really bring out the big guns, what some of the really popular techniques for much harder tasks like understanding speech or parsing music traces or things like that are neural network methods. So the RNN, of course, is the recurrent neural network, is built for modeling sequential data, and it works reasonably well on motion sensors. It has problems with longer-term temporal dependencies, which is why the LSTM, that's what the LSTM up there was invented. So the basic idea of these is they're neural network cells that each take in one input at each time step. They process it to update their hidden state, and then they pass along this understanding of the hidden state to the next time step, basically trying to model the progression of some unknown quantity throughout time as the sequence progresses. And these are generally harder to train and harder to use than some of the other methods, especially for something like sensor data, where you've got a lot of redundant cases. Even the LSTM has a lot of problems with modeling long-term temporal dependencies. And if you've got some 100 hertz signal where you're looking for something that, I picked up my leg 10,000 samples ago, and now I'm putting it down, and that could be a little bit hard to pick out something like that. So there's other methods, like the differentiable neural computers that are super hot these days. I'm not going to talk too much about these because they're way more complicated than the other ones. They would deserve like 3 talks by themselves. But I think that's all I've got. I can take some questions. Yes?
Is there a standard reference for figuring out both the accelerometer data and sort of what you went through, at least the classical methods?
You mean like a textbook?
Yeah, textbook or article, or just where's a good place to start?
That's a good question. Nothing jumps to mind. We used a lot of different research articles that have been published that have kind of described, because there's sort of multiple perspectives on the issue. There's this huge body of engineering text that is just signal processing, handling noise, understanding sensor data from like the last 50 years of interpreting signals and the way that we're designing filters and denoising and all of that. And then there's the sort of new wave of like machine learning for signals and understanding speech and things like that. And I actually think that the overlap of those and like a really good text that kind of starts with the signal processing basics and works up into more complicated machine learning approaches, I haven't been able to find something that really does that well.
Even something that suggests here's some useful featurizations that have been used with accelerometer data.
Yeah, I'd have to think. I don't have an example off the top of my head. I'm sorry. Yes.
How do you deal with sensor artifacts and outliers? Do you see them first, especially in motion? Do they screw up your classification analysis? And if you kind of omit them, what's your strategy for omitting them?
Yes, so it sort of depends on what the application is and what sort of classifiers you're using. Like big random outliers aren't really going to bias the summary statistics featurization all that much, but they might mess with dynamic time warping or with like a neural network approach. Generally, the filtering methods, like a Gaussian kernel, will smooth things like that out, but a really insane signal, a really insane point might totally bias things. But sometimes really weird signals in the sensor data can be indicative of strange behaviors. So I'd say it's an application-specific basis, a combination of filtering and using machine learning algorithms that are relatively robust to outliers tends to help solve those kinds of problems. Yes?
How do you validate your model? Do you run experiments with people?
One example, I think that probably is a good single example to answer that problem would be how we validate hard brakes. So we have different hard braking algorithms that we develop to track when someone is driving dangerously. And as part of our deals with insurance companies, we need to present a relative correlation between our hard braking algorithms and the predictions of their proprietary hardware that they would plug into the car, and that would directly monitor the wheels and track when they step on a brake. Those are the OBD2 devices. And so we would launch a long trial with the insurance company over the course of several months or even longer, where we'd track multiple drivers over time, and we'd get a sense of what's their number of hard brakes in some period of time from their device and from our device, and we would do an analysis of R squared based on that. And that's core to many of the, most insurance companies and usage-based insurance has that as a sort of standard metric. Yes? I'm sorry, could you say it one more time?
Have you considered going to car rental companies like Zipcar or Budget?
Yeah, actually, our current CEO was the former CEO of Zipcar. And we work with we've worked with a number of sort of large companies outside of the insurance space as well that I can't really give too many details about, but yes. Yes?
Different error properties or accuracy properties based on which kind of device or operating system your app is running on. I mean, I can imagine that if you're borrowing strength from other sensors or other apps, the Android is much better than the iPhone, for example.
Yeah, actually Android's much worse when it comes to motion sensors in general. They've got super high dropout and issues like that, and some Android phones don't even have gyroscopes. But yes is the answer, and it's a huge pain figuring out, I mean, because ideally, especially if we make a deal with an insurance company, we're going to have to, we've got some algorithm that we're going to be tracking people on. We need to prove to regulators who are, there's all these discrimination laws in insurance that we're treating each person the same, regardless of their financial status or something like that. But if an algorithm is performing differently on higher-end cell phones versus lower-end cell phones, you might think, oh, well, this regulatory agency is going to flag that. So that's a big focus of ours, is designing algorithms that work as similarly as possible on different types of phones. It's tough, because there's like 1,000 different types of Androids out there. We've got to do loads of testing, and we've got this like giant box of cell phones we test things on. And yeah.
As a follow-up to that, how concerned are you about the level of recruitment in your trials? In other words, if somebody knows that they have a sensor in their car, are they less likely to break hard frequently? And this sort of behavioral bias enters into your algorithm as a measurement component.
Yeah, so we've done a number of different tests on this with people and have different types of apps. We have some apps that are specifically for insurance. Sometimes we work with agencies like Applause where they'll just give testers your app, and they won't give them too much information what the app is, or they're just pay people to download your app or do things with it. And we look at the difference in braking and distraction and all of our different metrics in these different populations. And they are different. We see a decent amount of variation based off of what group of people they're in. When people have a financial incentive, which is a subsection of the populations we monitor, their behavior is significantly different. So we're aware of it, and we monitor it in different types of situations. Yes?
Do you do all the data preparation classification on the phone itself, or sending you the raw data only via server?
Yeah, so it depends on which algorithms we have. We have some that run on the phone and some that run on the server. That's sort of application specific. Running on the phone is nice because you can get instant gratification, and we don't need to pay AWS bills because we can use someone else's hardware to do it. It's bad because it burns loads of battery, and if you have a super large, you can't really put some 200 megabyte TensorFlow model on the phone in an app that's supposed to be a megabyte and a half. So these are tough things to balance. Yes?
Yeah, you mentioned that you are offering some Schiebler algorithms. And for Schiebler,
So do you mean for different applications and different types of? Yes, I mean this would be using the types of machine learning algorithms that that I'd mentioned would do generally pretty good job of modeling what patterns and signals in the sensors would be indicative of different metrics that we were tracking.
Yeah, let's say if you have like some distribution that you have already known, like maybe linear distribution. I think that's easier to kind of analyze that. Like we are generating some random or some complex signals. How can you summarize the pattern? How can you, yeah.
So I mean, really, it's the higher order machine learning methods and signal modeling methods will generally do that. I mean, if you fit a random forest, for instance, to sensor data, it is modeling a complex, nonlinear structure of that data. And it's the same thing with like the recurrent neural networks or even the dynamic time warping. It's just different models can model different types of situations. And some models are technically can model any kind of distribution, but generally it's hard to move it to model the exact distribution that you're interested in. Like any neural network model theoretically can model any function, but good luck training feed-forward neural networks to do a lot of things. Any more questions? All right, thank you very much, guys.